In this lecture, we will discuss the proportional control. In proportional control, the control signal is linearly proportional to the system error. The transfer function is a pure gain. It has no dynamics. Then the proportional controller will not change the type of the closed loop system. So let's consider an example. Let's assume the plant has a transfer function of a second order system. If you still remember, so the motor can be modeled by a second order system like this. So to determine the type of closed loop system, we can use G times D. So D is a controller. Here is just Kp. Then we can count the number of pole at the origin. Here, since the transfer function of D times G has no pole at the origin, therefore, the closed loop system is type 1 if the transfer function of the plant has this form. Then we know in the unity feedback, the denominator of the closed loop transfer function will be the numerator, the sum of the numerator and the denominator of G times D. So D is controller, here is Kp. Then we have the characteristic equation that will be the denominator of the closed loop transfer function. So if I write this equation in the form of standard second order system, so here is omega n squared. So omega n is a natural frequency. You can see here, we can change the value of Kp to change the natural frequency. And A1 will be 2 times that omega n. So how to calculate the steady state error for unit step impulse? We know here is G times D. Since it is type 0 system, so we can first calculate the position constant. So position constant, you just let S be 0. So we have the position constant here. Then the steady state tracking error for type 1 system will be 1 plus the position constant, Kp A over A2. Then it is A2 plus Kp A. You can see that we can increase the value of Kp to decrease the tracking error for unit step input. But no matter how large the KP is, there is still a non-zero steady state error. Then when we increase KP, we also decrease the damping. This is because large KP will give us small steady state error, but we know A1 is 2 times with omega n. So damping ratio with will be A1 over 2 omega n. So here's omega n squared. We have square root of A2 plus KPA. When KP is very large, then the damping ratio is very small. When the damping ratio is small, the overshoot is large. Therefore, large KP will make the transient performance has a very high overshoot. Now let's see a detailed example. Let's say we assign some values to A. Capital A is 1, then A1 is 1.4, so A2 is 1. Then we can calculate the transfer function for the closed loop system from R to Y. We know forward, the numerator is the forward path gain, it's KP, GS, then 1 minus the loop gain, then plus KP, GS, that is a closed loop transfer function. Here it shows the step response for unit step input. We can see that when we increase the proportional gain from 1.5 to 6, the steady state error is decreased. It also decreases the write time from 1% to 90%. But it increases overshoot. Now let's see how the proportional controller will affect the error due to a disturbance. Then the transfer function from the disturbance input to the error will be forward path gain will be minus GS. Let's assume V is 0, R is 0. Then 1 minus becomes, here we have minus, and 1 plus KP plus GS. Here I will not show you the detailed analysis, but basically, if we assume the disturbance is a step disturbance, then the step disturbance will yield a steady state tracking error in the same manner to the reference input. All the analysis is the same to the reference input. Then if this plant is beyond second order, so the analysis can be very complex. But in general, we have the principle, the higher gain of KP will decrease rise time, but at a cost of larger overshoot and less damping. Also, when we increase the proportional gain, it may lead to the instability of the system. So if the original closed loop system is type 0, then the proportional controller will not change the type of a closed loop system. Then the closed loop system is still type 0. For type 0 system, it has a non-zero steady state tracking error for constant reference input. It will also not completely reject the constant disturbance input.